Hi, Mitch Wenger back with another video on data analytics and machine learning. In this video, we'll discuss clustering using centroids. Hope you enjoy. Okay, let's get started. When it comes to clustering techniques, there are a lot of algorithms out there. Choosing which algorithm to use depends on a number of things: what type of data you have available, what is the purpose of your clustering application, and what are you trying to accomplish. The data mining team should choose the clustering technique carefully. As always, domain knowledge is beneficial. Clustering algorithms compare data objects with regard to their similarities and their dissimilarities. So here is a guideline for how to go about selecting the appropriate clustering algorithm. This was a paper done by Tan et al. In 2009. So you've got your data source, and then you select the data objects and attributes so that you can put together the data set you need for analysis. From there, you select the clustering method, what type of cluster, what's the structure of the clusters, run your algorithms and see your results. And you may repeat this for different clustering techniques. You may repeat it with the same technique, as we'll talk about in just a few minutes. Then you can go forward and validate your results, look at the features in the data set and see how they get clustered, maybe do some analysis of that clustering result. You've validated results, and you can then start interpreting what those results mean. How can you use that going forward in your data science efforts? And then you choose how to represent those results, generally through some type of explanation or storytelling. The most prominent clustering techniques are partition-based. Basically, we are going to have our data set with n objects in it, and we're going to divide it into k partitions. So as you can see, we need k to be less than or equal to n. Each partition then represents a cluster. So the data gets classified into these k groups. We've got a couple rules. Each group must contain at least one object. And conversely, in partition-based clustering, each object can only belong to exactly one group. So a general approach we can describe for this type of partition-based clustering is that we will arbitrarily start with some starting points, and then we will create that initial partition. At that point, we will try to improve the partitioning through some iterative approach. We'll relocate data objects from one cluster to another. We'll recalculate center points. The goal at the end and the criteria we evaluate are that we want objects that are in the same group to be close to each other. Objects in different clusters should be far apart from each other. So the method we'll talk about is clustering using what we call centroids. Centroids are just central points in each cluster. How many central points will we use? Well, we'll use k central points, of course. K-means basically says we're going to take our k, whatever k happens to be, and the data set. We need the data set, so those are the two inputs. In k-means, we start by selecting k data points as our initial cluster centers. Next, we look at each object in the data set and assign it to one of the clusters, whichever cluster happens to have the nearest center point. So we assign it to the nearest center point and assign it to that cluster. So that's the center point that is most similar to that data point. Next, we take all of the clusters that we've created and recalculate the mean value. And we now have a new center point for each cluster. And in most cases, especially after the initial assignment of the center points, the new mean value is going to change. Then we just start over again. We take our new mean values and work our way through the data set again, assigning each data point to one of those clusters. And we keep repeating that process until the mean center points for all the clusters no longer move. Basically, we have achieved an optimum solution, or we have reached the maximum number of iterations that we have specified. So you can actually limit how many times it goes through this. For you Excel power users, you may find that approach similar to how Solver works. So let's watch this animation and see what happens when we start our clustering process from various locations. You can see the initial selection of starting points, and then data points get assigned to each of the cluster centers. Once we've assigned all those data points, we recalculate that mean value, and you can see all those cluster centers move, and then we have to reallocate all the data points to those new cluster centers. What happens if we start from another set of points, or even another? Just watch and see. Now, in general, k-means clustering works best when the clusters are compact clouds in our data space and well separated. A lot of financial data tends to be sparse like that and have naturally occurring clusters. K-means is scalable and relatively efficient with large data sets. Now, as you can see, as you're looking at this animation, k-means often terminates at some local optimum. So it reaches an optimum based on whatever the starting points are. They may not necessarily be the overall optimum center points that are available. So therefore, we try to use random initial partitioning a number of times so that we have a pretty good level of confidence that we have achieved an optimal clustering solution. Another issue, the mean must be definable. So clustering is not very suitable for categorical attributes. And as you can probably guess, because we're calculating means, clustering through k-means can be sensitive to noisy and outlier data. Those outliers are going to affect those mean calculations, no matter which cluster they happen to be assigned to. So as you saw, where you start can make a big difference in your resulting clusters. As a result, it's often beneficial to run your cluster analysis many times using different starting points. You can actually compare the quality of your clustering runs by testing the tightness of your clusters and how well separated your clusters are. Now, k-medoids is a similar approach. Instead of taking the mean value as a reference, the medoid is used. And a medoid is simply the most centrally located data point in a cluster. So it's always going to be an actual data point. And the medoid is basically, if you think about a median for a group of numbers, a medoid is the analog of a median for multidimensional space. So the main idea is the same. We're going to find k clusters out of those n objects by first arbitrarily choosing our k objects as center points for each cluster. Each remaining object is clustered with the medoid to which it is most similar. And then the medoids get recalculated and iteratively replaced by a new data point as long as we can improve the quality of the cluster. So the idea is in both cases that we're going to minimize and reduce as much as possible the squared error value. Now, k-medoids is more robust because we're restricted to using an actual data point, so we're not going to have a mean that goes floating out somewhere in space because of an outlier. We're using an actual data point for the medoid value. Like we mentioned, k-medoids is more robust than k-means, but it is also more expensive from a processing standpoint. So that's something to keep in mind when you're doing your cluster analysis. For small data sets, it probably won't be that big a deal, but certainly for extremely large data sets, it's something to consider. And that's it for our introduction to k-means clustering. I hope you found it informative. Be sure to check out the other videos in this series.